Welcome to Applied Mathematics and Engineering. In this class, you're going to learn how to solve ordinary differential equations, ODEs, and partial differential equations, PDEs, using a variety of different methods in problems that are relevant to science and engineering. When you think about where do you see ODEs and PDEs in science and engineering, let's think about a couple of different fields. I've just written down a small subset of different fields in science and engineering that involve lots of ODEs and PDEs. Separation processes. How do you take a mixture of products or reactants and separate them? You need enormous energy to separate lots of mixtures of reactants and products because entropy is so high. The separation processes are governed completely by ODEs and PDEs. Same with transport phenomena, which includes fluid mechanics, heat and mass transfer, and they all include lots of transport of energy, of mass, of momentum that are all governed by ODEs and PDEs. The same is true for chemical kinetics and catalysis, process control and feedback, biochemical processes. The list goes on and on and on. But the point I wanted to make is that they are everywhere. As scientists and engineers, you will run into ODEs and PDEs across essentially all problems in your discipline. And so it's very important to know when you should use a particular tool and how to use a particular tool. And the purpose of this class is to teach you how to learn those tools. Now, as you can see, math and applied math is a very important subject in science and engineering. The goal of this class is to make you conversationally fluent in this language. And I like to think of math as kind of like a foreign language. The only way in which you get better is by practicing. And early on, it's going to be challenging, just like learning a new foreign language. It's very challenging. But the more immersion you have, the more practice you have, the better you'll get. What I like to tell my students is, you know how on your profile page for something like LinkedIn, there's a section on the bottom where you can write down your fluency level of any foreign languages that you might know. Beginner level, intermediate level, conversational level, native fluency. I don't think anyone's natively born speaking calculus. That would be a little bit scary. But the goal of this class is for you to become conversationally fluent in math, in applied mathematics, solving PDEs and ODEs, because math is the universal language that we use to speak science and engineering. It is the universal language where you can go anywhere in the world and people will know what you're talking about if you are solving a science and engineering problem. ODEs and PDEs, they govern various areas of science and engineering, and if you know that language, it is extremely empowering as a scientist and engineer. So, let's first get started by classifying a specific differential equations so that you can understand which tools might be used to solve that equation. To conquer the beast, you must be able to first classify the beast. 4 questions you need to ask a differential equation to be able to classify what kind of equation you're working with. Let's write those down. These are the 4 questions you need to ask when classifying a differential equation. Question 1, is it an ODE or a PDE? Ordinary differential equation versus a partial differential equation. Second question, what is the order of the differential equation? The third question, is it linear or nonlinear? Lastly, is it homogeneous or non-homogeneous? Let's start with classification number 1. Is the equation an ODE or a PDE? Let's write it down. Okay, so the first classification question you need to ask yourself is the differential equation an ODE or a PDE? For ordinary differential equations, the function you want, which might be a temperature profile, a velocity profile, a species concentration profile, depends only on a single independent variable. It might be position x, where you are spatially along an x direction, or it might be the temperature as a function of time, t. In either case, it only depends on a single independent variable, like usually position along some coordinate or time. In contrast, a partial differential equation usually has more than one. So a temperature profile that you might want to solve for depends on position x, y, z, because we live in a three-dimensional world, and it can also depend as a function of time. So the function you want, temperature profile, concentration profile, depends on more than one independent variable. If you're doing a 1D problem, it might be a function of position x and time. It's still a PDE because it depends on two independent variables of x and time. Derivatives only appear with respect to a single variable with ODEs. So I've written an example here. We have a second derivative with respect to position plus a sine x is equal to 0. So this differential equation only has a derivative with respect to x, the only variable that f in this case depends on. That's an ODE. In contrast, with partial differential equations, you get multiple derivatives with respect to different independent variables. So this is an example of what's called the heat equation, where we have on the left-hand side a partial derivative of your function with respect to the time t is equal to upside-down triangle squared is a Laplacian, and in rectangular linear coordinates in 3D, you just have the partial derivatives of x, y, z added together, the second derivatives of each of them. So this is an example of a partial differential equation. So the question of ODE versus PDE is a pretty easy question that's not so hard to capture whenever you have a differential equation. But this is the number one question you should ask first. Let's move on to the second question of order. What is the order of a differential equation? Okay, so now we like to talk about the order of a differential equation. And it's also pretty easy. The only question you need to ask is, what is the highest order derivative in the differential equation? And the best way to understand this is to just do a couple of examples. So let's suppose you needed to solve this differential equation up here. Example number 1. You just look at this and think about what is the highest order derivative in this equation. It would be this term, and it's a second derivative, which means that this equation right here is a second order differential equation. Let's keep going. We'll just do it pretty quickly. Next equation right here. Again, you go to the derivative, which in this case is the first term. The order of that is a single derivative in time, and therefore this one is a first order differential equation. Notice that the second term here is f squared. It's a nonlinear term. It doesn't matter what the square is. You just count the number of derivatives. Go to the highest derivative term, which in this case is just the first derivative. Now, third example, y double prime plus y is equal to 0. I often use this prime notation, and in fact, a lot of people in textbooks will use them. The prime notation just indicates a derivative. So in this case, a second derivative with respect to position. Same thing, you go to the first term, it's second order. Pretty easy. Okay, let's go to the final case here. We have a second order derivative here, y double prime. The whole thing squared plus y is equal to 0. Now think about what is the order of this differential equation. Although you have a square, it's still a second order equation because all you have is two derivatives of y. It doesn't get elevated to a fourth order differential equation just because you have a square, right? This is just y double prime times y double prime. It's still a second order differential equation. Okay, so through these examples, I think you got a sense of how to determine the order of a differential equation. Let's move on to the third one of linear versus nonlinear. Let's move on to the third classification question you should be asking, which is the equation linear or nonlinear? The question you should specifically ask is, does the function you want, temperature profile, velocity profile, concentration profile, and or its derivatives, t prime, v prime, c prime, as the derivatives of the function you want, do they appear in nonlinear forms? If no, it's a linear differential equation. If you have just even one term that appears in nonlinear forms, then the answer is yes, it is a nonlinear differential equation. Now, let's do again a couple of examples because that's the best way to figure out how to understand this classification. First example, dy dx plus sine y is equal to 0. Now, y is the function you want. Y is a function of x. And now you ask yourself, does y or its derivatives, like dy dx, appear in nonlinear forms? The first term here, that's linear because the derivative is a linear operator. But the second term over here, sine y, is a nonlinear function. You know what a sine looks like. It's got waves, it goes ups and down, it curves around. It's nonlinear, it's curvy. Therefore, this differential equation is a nonlinear differential equation. Now, second example. Identical to the first case, except I've swapped out the y with the independent variable x. In this case, that makes all the difference in the world with this question. Because all we care about is the function you want, which is y in this case. The independent variable, x, time, can appear in any form it wants to. It could be linear or nonlinear. So sine x is a nonlinear function of x, but it doesn't matter. It doesn't matter to us because all we care about is the function we want, which in this case is y. So you just look at y. In this case, it's just dy dx. That's the only form of y that appears in this equation, and that's a linear term, and therefore this differential equation is a linear differential equation. Next example, down here, we have x to the fifth, d squared y dx squared plus xy is equal to 0. Again, focus only on the function you want, which is y. So y appears as a derivative here, which is fine because a derivative, again, is a linear operator. This appears in a linear form. The second term, x times y. Y is a linear form. Therefore, this equation is a linear differential equation. Again, you can have x to the fifth, which is nonlinear, but we don't care because x is an independent variable. And you can have x to the fifth multiplied against d squared y dx squared. It's still a linear term. Now, let's do the fourth example. We have y times y prime, so that's dy dx, plus x is equal to 0. Now, we have a product of y and its derivative, y prime. Therefore, according to this definition, y times y prime is a nonlinear function. It's a quadratic, right? It looks like a parabola, y times y prime. And therefore, this is a nonlinear differential equation. It turns out that this question of linear versus nonlinear is oftentimes the main question that determines whether a differential equation can be solved or not. It turns out we have a lot of techniques built over hundreds of years of human intelligence and knowledge to solve linear differential equations. We have a bunch of tools. But nonlinear differential equations, we have very, very few tools available for us. And in fact, most of the nonlinear differential equations in science and engineering are solved numerically. And of course, this is just the way it works, but many problems in science and engineering are inherently nonlinear. There's a famous equation called the Navier-Stokes equations in fluid mechanics. That is a nonlinear differential equation. And the nonlinearity of that equation is what creates turbulence and chaos and tornadoes and massive wind currents and atmospheric changes and currents within the ocean. And so those problems are actually extremely difficult to solve because they're nonlinear differential equations, and we have very few tools available to us to analytically solve those equations with pen and paper. When I say a numerical solution, I mean solution to a differential equation on a computer. You can numerically evaluate derivatives, use a software to find the solution to the equation, but out comes a bunch of numbers. You'll get a vector or matrix of numbers. You can't write down y of x is equal to this on a pen and paper. That would be called an analytical solution. So for most of this class, we're going to focus on analytical solutions to differential equations, things that you can write down on a pen and paper. There's a whole separate beast out there of numerical techniques, which is a whole separate course on how to solve differential equations using a computer numerically. Okay, so this is linear versus nonlinear. Oftentimes, the main question that will tell you whether it is futile for you to keep going and analytically try to solve that equation, or worthwhile to keep going and try to solve it analytically. Okay, let's move on to the fourth and last question about classification, homogeneous versus non-homogeneous equations. So the final question you should ask yourself with classifying a differential equation that you would like to solve is the equation homogeneous or non-homogeneous? And it's a very simple rule. Essentially, you ask the equation, does f equals 0 solve the equation? So f in this case is the function you want. Temperature profile, velocity profile, concentration profile. You want to know that function as an engineer. Does setting that variable equal to 0 solve the equation? If the answer is yes, it's homogeneous. If not, it's non-homogeneous. Let's do some examples. F prime plus sine x equals 0. You set f equal to 0. This term is gone. Sine x does not equal 0. Therefore, this is non-homogeneous. Next example, f prime plus x times f prime plus f squared is equal to 0. You plug in f equal to 0, 0, 0, 0, 0 equals 0. Great, it's homogeneous. Pretty easy, okay? So there you have it. Those are the 4 classifications that you need to think about when you first see a differential equation. Based on the answers to these 4 questions, the tools that you use to solve that equation could completely differ. So it's very important for you to first understand what it is that you're working with. What equation are you working with? After that, you can say, oh, with this equation, I can use A, B, C. These techniques will work, but D doesn't work because of these reasons. And so you need to be able to classify the equations first to understand how to solve them. Now that you know the 4 different classification questions you should ask, let's do a couple of summary examples and ask these 4 questions for these examples. First example, this one right here, this top equation. Let's go in order. First question, ODE versus PDE. Well, we have a normal derivative of f being only a function of x. Therefore, it depends on only a single variable. Derivatives appear with respect to only a single variable. Therefore, it's an ODE. What is the order of the equation? You go to the highest order derivative, which in this case is the first term right here. How many derivatives? There's 2 derivatives, and therefore, it's a second order equation. Next question, linear versus nonlinear. First term, it's linear. It only appears as the second derivative of f. Second term, also linear. Third term, f squared. That's a quadratic. It's curved. It's not linear. Therefore, it's a nonlinear differential equation. And finally, the fourth question, homogeneous versus non-homogeneous. You set f equal to 0, 0, 0, 0 is equal to 0. Therefore, it's homogeneous. Okay, easy peasy. Let's do the second example. ODE versus PDE. We now have the function f, which is the function you want, depends on x and y, and there are derivatives with respect to x and y, and therefore it's a PDE. The highest order derivative, in this case, is a 4th derivative in both x and y, and therefore this is a 4th order differential equation. This kind of equation often comes up with bending. Beam bending often has a 4th order term just like this. Now, next question. Linear versus nonlinear. Remember, we want to get f. F is the function we want. A lot of students get confused over this because we've been using y as an example. Y was the dependent variable, but in this case, f is the dependent variable. X and y are both independent variables. Therefore, even though y appears as a nonlinear form over here, in this equation, f is the function you want. So we don't care about x and y and how they appear as linear or nonlinear. We care about f. Does f and its derivatives appear in linear forms or not? The answer is it's linear because both of these first two terms are linear functions of its derivative. And therefore, it's a linear differential equation. And finally, is the equation homogeneous or not? You set f equal to 0, left-hand side is 0, the right-hand side non-zero, therefore it's non-homogeneous. Okay, I hope you understand the basic 4 rules of classifying differential equations. And with that, you're on your first step towards understanding how to solve that equation, or what tools you can use to solve that equation. So we're now going to move on to actual solution procedures. And we're going to start with the most simple case, first order linear differential equations. We're going to go through a solution procedure that you've probably already seen before, but we're going to do it anyway as part of the review. Okay, now that you know the 4 different classification rules that you should think about with a differential equation, you might be wondering, why do we have to do that? Why do we have to classify? Can't we just solve it? Yes, but you need to be able to classify and understand what kind of equation it is for you to know which tools you can use. For example, let's move on to actual solution procedures for the simplest kinds of differential equation that you'll cover in this class. Linear first-order ODEs. Again, 3 out of the 4 classifications already came up. It's an ODE, first order, linear. Okay? Any means it could be homogeneous or non-homogeneous. It could be whatever it wants. So as long as it is a linear first-order ODE, those right, 3 out of the 4 classifications, the equation is going to have the following form. We have a first derivative. F is the function you want. It appears in linear forms only. And it's a first-order equation. And like I shown here, the right-hand side, g of x, can exist or not. If it exists, it's non-homogeneous, but it doesn't matter. That's why I wrote any linear first-order ODE. For this case, there's a very convenient solution procedure that I know you've already know and you're using, but we're going to derive it from using a simple little derivation here. So we're going to first rewrite this equation in just a small little minor way. Just like that. All I've done is to take this differential element dx, multiply it across to every term. Now, we're going to suppose, we're going to make a guess, there is some function, capital F, which we'll define in a little bit, that we can multiply across every term. That's what we're going to do next. I've just taken the equation up here, multiplied each term with this capital function f of x. Now, what we'd like to do next is to consider a differential of f, the capital F, and little f, the function we want. So we've just taken the product rule of the differential of the product of little f, the function you want, and some function capital F of x. Of course, you just use the product rule, and you get the expression on the right. Now, when you think about our original equation, you can see that this first term already looks just like the first term from above. And the second term almost looks like the second term from above, with one condition. Okay, so we're matching like terms. This second term almost looks like this term from above if this increment d capital F is equal to the term inside the bracket, then these two equations are matched. The terms are matched. So I've posed the question, what if this increment df is equal to the term inside the brackets from the left over here? If this is true, we can map this bottom equation with the differential equations that we have right now. So let's take this equation, integrate both sides, and find f as a function of x. I've just brought the capital F over onto the other side. We can just integrate both sides of the equation, and out comes this equation right here. You get a log f on the left-hand side. You get the integral of p dx on the right-hand side. You take the exponential of both. Boom, out comes this expression right here. Now, you've probably seen this before. It's called the integrating factor. OK, so you've seen this before, the integrating factor. So now, if this f exists, because we've speculated that it exists, which you can find from performing this integral, this exponential integral, and then now we know what the identity of f is, so we can proceed. So we know that there's a mapping here where the left-hand terms here can be mapped to capital F times d little f plus little f times d capital F. Therefore, the entire left-hand side is just given by this expression below. So now we can then rewrite that as just the total differential d of the product of little f and capital F. So the left-hand side, I've just replaced it with d little f capital F, because if this is our capital F, then this term here, the second term, can just be replaced by little f d capital F, and therefore that's all you get on the left-hand side. Right-hand side, I've just taken this equation, this right-hand side, this non-homogeneous term, brought it straight down. At this stage, we can integrate both sides of the equation. And once you integrate this on both sides of the equation, you get out a beautiful solution to a first-order linear ODE. OK, we've just finished integrating. So all I've done here is to integrate both sides of the equation. This right-hand side just drops straight down. On the left-hand side, you get little f times capital F. I've divided both sides by capital F, and out comes this equation. I've added a c, which is a constant of integration. Of course, when you integrate a function, you get a constant to pop out. And therefore, that is your constant of integration. Usually, you would obtain c through an initial condition or a boundary condition that's given alongside the problem. Now, this is it. This is the solution to all linear first-order ODEs. It always works. So if the 3 out of the 4 questions are ODE, first order, linear, you are guaranteed that this equation will always work. So if you have these 3 lined up in your classification, just go straight to this equation, and this will always work. It will always work. Okay? So maybe we'll just do a quick example of this first order linear ODE example, and then move on to different types of first order ODEs. Great, let's finish off this first order linear ODE solution procedure with a brief example. I've retained the main equation form and the solution. We would like to use this solution procedure on this following example. X squared df dx plus 2 times f is equal to 5x. It's linear, it's an ODE, and it's first order. Boom, this could apply. First, to rewrite it into this generic form, let's divide through by x squared and see what we get. OK, let's multiply through with dx, rearrange some equations. OK, all I've done here is to multiply through by the small little increment dx. And now we're going to, again, assume there exists some function capital F that we can multiply across. And now we know what f is. It's just the integrating factor. In this particular example, we have a p of x, which is this function right here. It's just 2 over x squared, because you can see the mapping. It's df dx plus 2 over x squared, which is your p of x, times f is equal to 5 over x, which is your g of x, the non-homogeneous term. So like we did earlier, this term in the bracket is equal to the small differential d capital F, which ultimately gives us the integration factor. The integration factor for this particular example is simply e to the integral of 2 over x squared, because that is our p of x. You just straightforward integrate, you get negative 2 over x. This is our integration factor. So now with this, we have our solution. You just write it down. We replaced our differential on the left-hand side in this form. We integrate both sides. And out comes our solution. Good. So there we have it. We have our solution f of x, which is the function you want, is equal to the stuff on the right-hand side. Of course, we have a constant of integration c, and we just follow the procedure, and it's pretty easy. The first order linear ODEs, pretty easy to solve. Now, this integral is actually a unique integral. It's called the exponential integral. There is no closed form analytical integral of this, and generally you have to plot it numerically. So in this case, you don't have to keep going and actually try to integrate this equation. You won't be able to do it analytically. So MATLAB and Python and a lot of softwares have a built-in function called the exponential integral. And that just simply will evaluate this integral numerically for you. So even though you can solve equations analytically, like the way we did here, there are many situations where it will involve a complicated integral that you can't reduce furthermore, right? You can't just keep going and reduce it into a clean analytical form. That's perfectly okay. The fact that you can write it as f equal something that you can write down on paper is a major step in understanding how that system or problem might behave in a real science and engineering application. So if you can get to this form, you've made a lot of progress analytically. With that, that concludes linear first-order ODEs. And from here, we're going to move on to different types of solution procedures for first-order ODEs. At this stage, we've covered how to solve linear first-order ODEs. You solved the linear case. The equation can be written over here on the left-hand side. You can always use the integration factor technique, and that will always work. First-order ODE, left-hand branch, completely conquered. Now, there's a whole other branch, which I've drawn here on the right-hand side, which requires different techniques, because if it's a nonlinear first-order ODE, the integration factor technique will not work. And this tree diagram is incredibly helpful. I find it incredibly helpful for figuring out which tool you can use. Now, when you're unlucky and you have a nonlinear first-order ODE, then the next question you should ask is that equation separable? And we'll talk a little bit about what separable means. If it's separable, that solution is what I would like to call easy or trivial, which is great. I'll show you what we mean by separable very shortly. You probably already have done it many times from your high school calculus class. You just didn't know that's what it meant to be separable and where you were along this tree diagram. Now there's a whole other side of not separable that we'll talk about next time. But for today, let's suppose you have a first-order ODE, it's nonlinear, and let's ask whether that equation is separable or not. What does it mean to be a separable ODE? A separable ODE is an equation that can be written in this way. You have some function that you want to find, f, as some function of the independent variable x. If you can write it as some function of g of x times another function h, which is solely a function of f, so you've separated x and f and wrote it in this form. If you can do that, the equation's separable. If you cannot, it's not separable. Suppose it can be written in this separable form. Then the solution is very easy to do. All you need to do, bring all the f's on one side, all the x's on the other side, and integrate both sides. All I've done is to bring h of f on the left-hand side, kept the g of x on the right-hand side, multiply it through by the small increment dx. We just now integrate both sides. And after that, you would just solve for your function f, and that's your solution. Let's do an example to solidify this solution procedure. OK, suppose you wanted to solve this equation. 3 times y squared dy dx is equal to cosine x. The function you're looking for is y. Depends on x. Clearly, it's first-order equation. It's nonlinear because you have y squared, and y squared is a multiply against dy dx. So we're definitely on this right-hand side of the branch, but we can separate them. We can write all the y's onto one side, all the x's onto the other side. So we can separate them and directly integrate. Just like that, integrate both sides. All we did was direct integration. Y cubed is equal to sine x plus a constant of integration. You can leave it in this implicit form if you want. You could take the cube root and find y as a function of x. So it's what you want. In a differential equation solution, you want to be able to solve for your dependent variable as some function of your independent variable. And there you have it. So whenever you have a first-order ODE, it's nonlinear. It's not the end of the world, because if it's separable, it's very easy, just like I've shown you here. OK, so that's it for today. Next time, we're going to do this branch, where if it's first-order ODE, nonlinear, not separable, what do you do down here? We'll cover that next time. See you then.